Let's talk about set cover. Uh, let's talk about the greedy approximation algorithm, and I'm gonna go through the proof, and I hope that's gonna help you follow. I hope you follow along, and I hope it's gonna help you on the weighted set cover problem on the homework. So let's get into it. So here we are given a set of elements, such that we have these sets. We have a set of elements where we split the elements into sets, right? And we want to pick a selection of these sets S such that the union of those sets contain the n elements we had. And we want to minimize the number of sets that we pick. So if we were to actually find the optimal solution, what's going to happen is that it's going to be an exponential time algorithm. Whereas if I were to use this greedy algorithm, where until all these sets are covered, until all the elements are covered, we're going to pick the set with the largest number of uncovered elements. Right. Ooh. Right. The important part is we're talking about largest number of uncovered elements, and that's going to be our greedy heuristic. And so I've defined that we have n elements. We have k as the optimal number of sets to cover all n elements, and that we have u of si is going to be a number of uncovered elements in S of I. Usually this is at some point in time, so some iteration. Okay, so I is going to be the number of iteration that we pick this set of S, right? So our goal is to prove that this greedy uses at most k log n sets. So here is an example. We have 14 elements. We have 5 sets. And the optimal set is going to be, that cover everything, it's going to be A1, A2, right? Where the two sets, k is 2. That's our optimal solution. However, our greedy solution is going to take the one with the largest number of uncovered elements. And the first thing that happens is, so in the first iteration, we're going to pick B3 because we have 8 uncovered elements versus the 7 in the optimal sets. After we have picked 8, we now move on to the next iteration where we have A1 and A2 both now have 1, 2, 3 elements uncovered, but B2 has 4. So we're going to take B2 next, and then now we can just take, now at this point we'll take either B1, A1, or A2. But either way, our greedy solution is going to give us 3 elements, 3 sets. Okay, so suppose that I have, at the very beginning, I have n elements, and I'm going to take S1, right? The set S1. And so I'm going to say that the number of uncovered elements in my first iteration of the sets we pick is going to be greater than equal to the number of elements remaining that we have, which is n at this point, over the k optimal sets. And let's see why we have this inequality, right? So let's build some intuition. So in the first iteration, we're going to pick this with 8 elements, right? So 8 over 2, we have 4. Okay, so hold on. Yeah, so we pick 8 elements, and 8 is greater than or equal to 14 over 2, which is 7, right? And so what happens if, suppose I don't have B1, B2, or B3? If I don't have that, I just pick A1 or A2, right? If I were to pick A1, A2, then we have U of S1 equals to N of K. This occurs if and only if all elements, all Si, is equal to N over K for I in 1 to K. Right? If the largest set that I pick is 7 elements here, then the rest of my optimal sets, they all have to contain 7. Otherwise, I can't cover all n elements, right? Because if I don't have 1, 2, 3, I'm left with A1, A2, and both of them have 14 over 2 equals 7 elements uncovered at each iteration of my set, right? I take A1, next iteration I have A2, and that only has 7 elements uncovered as well. Okay, so this inequality is going to be equal if and only if all my optimal sets have n over k number of uncovered elements at every iteration. Or sorry, not every iteration. Just saying that all my uncovered sets will have n over k elements that we cover. Right. Now, what if we have a contradiction? Proof here. Proof. Suppose that we only have the very first set that we pick has less than n over k. Right? Suppose this occurs, and what does this mean? This means that, remember that the number of uncovered elements for all sets from 2 onwards, this must be less than or equal to the number of uncovered elements in S1. Right? Because otherwise, I would have taken one of these sets if the number of uncovered elements was greater than the number of uncovered elements from the first set that I pick, right? Like if this were 6, I wouldn't have picked B3. I would have just taken A1 and A2 because there were 7 uncovered elements versus the 6 here instead. So if this is the case, then you have all these sets that are also smaller than. So this means that all the number of uncovered elements are also smaller than n of k, right? Onwards. So if all these elements are smaller than n over k, you can't possibly cover n elements with k sets, right? So this means that we can't cover n elements with k sets. So, but that's a contradiction because k is the optimal number of sets, and that means it can cover everything. So here we have a contradiction. So now this inequality that we have is going to be true, right? And this is going to be true for every set that we pick in any iteration afterwards, which I will show you why over here. So let's define n of t as the number of remaining elements after t iterations of our greedy algorithm over here. So let's look at, so we know that n of 0 is going to be n, right? At the very beginning, we're going to have n uncovered elements remain. So now we're going to look at n of 1. n of 1, right, is going to be the number of elements we had in the previous step minus the number of uncovered elements from S1, right? So if I pick S1, then the number of elements remaining after the first iteration is going to be the number of elements we had originally minus the number of uncovered elements that I just took with the first set. And since this is greater than or equal to n over k, we can say that this is going to be less than or equal to n0 minus n over k. And we know n is n of 0, right? So if this inequality is greater, subtracting it is going to give us this inequality. And on this side, we're going to get n of 0 as 1 minus 1 over k. Now let's see what happens when we do an extra step. We have n of 2 is going to equal to, right? Here we're going to have this number of elements remaining after the second iteration is going to be the number of remaining elements after the first iteration minus the number of uncovered elements in the second set we pick. Okay, let's see what's going to happen. If I take k sets, if k is my optimal number of sets, right, then after the first iteration, I should be able to cover the remaining elements with k minus 1 remaining sets left. Or you can call this, or you can just kind of call this L, right? N1 over L, where L is the number of remaining elements left after the first iteration. Oh wait, sorry. L is the number of optimal sets that we can cover the number of remaining elements left after the first iteration. Okay, so what we know is that, so this is going to be N1 of 1 minus 1 over k minus 1. So let's see what's going to happen. If I increase k minus 1 to k, this fraction is going to decrease, and so this entire term is going to increase, which means that we can upper bound this term by 1 minus 1 over k. And now we have this n1 is less than or equal to this term over here. I subtract that in. We have an inequality of 1 minus 1 over k to the power of 2. Now, if I were to do this by an n3, we're going to get n of 0 as 1 minus 1 over k to the power of 3, which means that for some iteration t plus 1, it's going to be the number of remaining elements at the t plus 1 iterations is going to be equal to the number of remaining elements after t iterations minus n over t over k, right? This is the inequality from the book. And since we can apply this logic to n of 0, we can keep substituting terms in, and we're going to get n of 0 as 1 minus 1 over k as t plus 1, right? So let's make it kind of easier. Let's just use t. So at the very end, we have n of t is going to be less than or equal to n, the number of remaining elements in the very beginning that we want to cover, multiplied by 1 over k to the power of t. So let's find out. So we want to know how many number of iterations it takes for us to get less than one element remain, right? Which is the same as saying, when do we cover all the elements? So in order to cover all the elements, let's have this inequality here. We substitute this in. And now let's look at this inequality that we have. Let's make use of this relation. If 1 minus x is less than or equal to e to the negative x for all x, and equal if and only if x is 1, right? So this 1 minus x is e to negative x, and then equal only at this point. So in this case, our x is going to be 1 over k. So we now have n of e to the negative t over k is going to be less than 1. Let's take that to the other side. Log both sides. We're going to get 1 minus log of n. So this is 0. And now let's take the negatives. Let's flip the negatives over. So we now have t of k is greater than log of n, and t is greater than k log n. Okay, so we know that the number of sets we're going to take is going to be greater than or equal to k log n. That's when we have no elements remain. Now, when does it equal 1, right? Let's think about this. If I substitute this term into this, the t here, we're going to get negative k log of n over k, right? So this is going to be equal to n to the e to the negative log n. I flip, I'm going to take the n down and the e up there of the log property. I'm going to switch these two. And now this is going to give me, right, so this is negative 1. I'm going to get this term, and I get equal 1. So we know that after this many iterations, we only have one element remaining. So let's just take one more iteration, and you're always guaranteed to have 0 elements remaining, right? Need k of log n plus 1 iterations or sets. Ooh, I'm running out of battery. Or sets, right? To cover all the elements. So we know that, okay, so if it takes this many sets and iterations to cover all our elements in this greedy heuristic, then we know that the number of elements that remain is going to be the number of sets, the cost that we need is going to be upper bounded by k log base e of n.